So let's go once more into the logistic map with a goal of trying to use both our knowledge about calculus and iteration and how it's related to derivatives and stability and that kind of thing, as well as using Mathematica to help us really try to problem solving here and try to understand logistic map, and in particular bifurcation diagram, ultimately Feigenbaum constant, the first Feigenbaum constant at least. So this is meant to be an illustration of, for example, how I might go about exploring a topic, and hopefully an encouragement to you to gain skill at exploring the topic. Again, combining both knowledge, symbol skills, algebra, calculus, and technology use. Our logistic map with parameter mu is f sub mu of x equals mu times x times 1 minus x. Mu is our parameter. This is a one parameter family of functions that we want to iterate. P sub n equals f sub mu of p sub n minus 1. Generates a sequence. If we start with a seed P0, it gives us numbers P0, P1, P2, P3, etc. And we're interested in knowing what happens to that sequence for different values of mu. And the bifurcation diagram that we're trying to work on making here is supposed to help us understand what's happening as mu changes. How does the value of mu affect what you observe? Okay. So what kind of techniques do we know to do so far? We know about making the cobweb plots, which, by the way, you can do on a TI calculator, graphing calculator. Maybe I'll have time to show you that. Make the cobweb plots, look for fixed points, try to analyze the fixed points. This being the logistic map is actually not the exact same example we did last Tuesday, a week ago, where we had the population of fish model. It's similar, but it's not the exact same thing. Remember, with that model, the fixed points, the parameter was called k, and the fixed points were always 0 and 1, no matter what k was. We talked about the logistic map, I guess it was 12 days ago, almost 2 weeks ago, and a little bit a week ago. Its fixed points, well, one is always 0, but the other one depends on the parameter mu. Let's reinforce what those are again. So we want to set f sub mu of x not equal to 0, but equal to x, right? If we're after fixed points. That's a common mistake. If I ask you to find a fixed point of a function, don't set it equal to 0 and solve for x, set it equal to x and solve for x. Okay. Keep track of what you're doing. You're looking for a value of x where the input equals the output. You still get a quadratic equation to solve, but it's got x on one side. If you want to use the quadratic formula in general, you'll need to get 0 on one side. So in this case, we need to subtract x from both sides. And if you do so and factor out an x, you get this. And fortunately, you don't have to use the quadratic formula, though it's not a problem if you do have to use it. This, since it doesn't have a constant term, is pretty easy to factor. Factor out an x, and you get this. Oops, forgot a mu in there. So your fixed points are x equals 0 is one of them, where that one's 0, and where this term is 0, and that's going to be, again, mu minus 1 over mu, which, by the way, you could also write as 1 minus 1 over mu if you like. And when mu is positive, well, and in particular bigger than 1, if mu is bigger than 1, here's the situation. You got the line y equals x that you want to draw in there as well, as you always want to do with cobweb diagrams. Mu is bigger than 1. Mu is the slope of the function, by the way, at x equals 0, right? The coefficient of the x term would be the same as the slope of this function when x equals 0. In fact, the derivative here, f mu prime of x, differentiate this, you'd get mu minus 2 mu x, plug in 0 into that for x, and you get mu. Mu is the derivative of this at 0. So if mu is bigger than 1, then the slope of the curve at 0 is bigger than 1. It's got to go above the y equals x line. The original function can be factored. In fact, that's how I wrote it right at the start. In this way, its roots are 0 and 1, no matter what mu is. And it's when mu is positive, its maximum value is going to be when x is a half. So here's a generic picture that you might get when mu is bigger than 1. There's 1. There's a half right there. It does reach its maximum value when x is a half. Maybe that's worth calculating here. What is f sub mu of 1/2? Plug it in the factored form. It's mu times a half times 1 minus a half is another half. Mu over 4 is the maximum value. That's actually worth knowing for a certain purpose. Mu over 4, one purpose that's worth knowing is that it helps you confirm that as mu increases, this graph does go higher. Mu is like a vertical stretch. Think about the formula. You graph x times 1 minus x, it's an ordinary. Probably you might say with x-intercepts at 0 and 1, increase mu away from 1 is stretching it upward. If mu is 1, that max value is 1/4. But as mu gets bigger than 1, it goes higher than 1/4. So that's the basic picture. This point right here has coordinates equal to mu minus 1 over mu for both x and y. I'll just label it on the x-axis there. That is mu minus 1 over mu right there. We know, based on what I told you, it's not an official theorem in the book, that the stability of this point, whether it's attracting or repelling, depends on the derivative of f at the value, at the fixed point, whether it's between -1 and 1 or not, right? Remember that? Which is related to one of the theorems in the book. It's related to the contraction mapping theorem about when a function has a unique fixed point. Yeah, remember that? We'll talk about it again. It is related to that theorem. If I plug this fixed point, well, let's plug 0 into the derivative. If you plug 0 into the derivative, you get mu. And when mu is bigger than 1, that's going to be bigger than 1. The fixed point at 0 is repelling, unstable. Which makes sense if you think about starting with a seed near 0 and doing what you're supposed to do with the cobweb diagram. You're going to go away from 0. If your seed is close to 0 but positive, say, you go up to the graph, then over to y equals x, up to the graph, over to y equals x. You're going away from 0. If you plug in a negative number, the same kind of thing happens. You go down to the graph, over to y equals x, down to the graph, over to y equals x. You're still going away from 0. 0 is repelling. 0 is a repelling or unstable fixed point when mu is bigger than 1, which is the main example we want to think about, is when mu is bigger than 1. You can think about what happens when mu is less than or equal to 1, but we're focused on what happens when mu is bigger than 1. It's more interesting when mu is bigger than 1. What about the other one? Yeah, this one now. F mu prime of mu minus 1 over mu. Plug that into the derivative, you get mu minus 2 mu times mu minus 1 over mu. Simplify, divide out the mu's. Looks like you get that. Ultimately, you get 2 minus mu. The fixed point at mu minus 1 over mu is going to be attracting when this is between -1 and 1. When will that happen? When mu is between 1 and 3. If you want, you can graph this as a function of mu. Graph 2 minus mu as a function of mu. It's a straight line with an intercept, a vertical intercept of 2 and a slope of -1. It's between -1 and 1 when mu is between 1 and 3. For mu between 1 and 3, that's where the output of this function is between -1 and 1. Yeah, mu minus 1 over mu is an attracting, also called stable, fixed point. FP again means fixed point. If mu is between 1 and 3. And it would be repelling unstable if mu is not between 1 and 3. Well, okay. That's not quite right. For sure, if it's repelling if mu is strictly bigger than 3 or strictly less than 1. Actually, when the derivative has an absolute value equal to exactly +1 or exactly -1, we don't officially yet have a theorem that tells us what happens. And in fact, in general, different things can happen depending on the example when the derivative equals exactly +or -1. Remembering these things now? We're reviewing things we've learned before. I've done these calculations before already, but I think it's worth doing again. Okay, let's start getting Mathematica to confirm these things, because we're also going to use Mathematica to do more complicated things here today. And you got Mathematica open. If you've got your computer with you, you can work along with me. If you prefer, you can also just watch me work and think about it, and maybe watch part of the video sometime tomorrow if you want. First of all, I like using the subscript button here in the writing assistant, which you can get to through the palettes menu. F sub mu of x. Okay, so I'm making, again, the parameter mu a subscript, which is fine to do here in Mathematica. And the variable itself is inside the square brackets. So I've got mu times x times 1 minus x. Enter that. That's my logistic function. And I had quit the kernel. That's why it's taking a while to get going here. Yeah, I did escape, M escape to make a mu. Escape, M escape makes a mu. Sorry about that. Oh, I wanted to show myself here. Escape, M escape makes a mu. So there's our logistic map. If all we're after is just iteration, the quickest way to see some iterates is to use NestList. NestList. Pick a value mu between 1 and 3, like 2, say. Pick a seed like 0.1, pick the number of iterations, say 20. And we see when mu is 2, that it looks like your fixed point is at 1/2. And it's attracting. If mu is 2, then yeah, mu minus 1 over mu is 1/2. If mu is 2.5, Then mu minus 1 over mu is going to be 0.6. 0.6 is an attracting fixed point. If mu is 2.9, then mu minus 1 over mu is 0.655172. That should be an attracting fixed point, though it may take longer to reach it, so to speak. Right? We've seen this before. NestList, capital N, capital L. Put the function name there. Notice I'm not putting the X in there. It's a problem if you do that, I think. I'm just putting the function name, the seed, and the number of iterations. And this is just mu minus 1 over mu. I'm just trying to predict what the fixed point is. We can see after 30 iterations here, we're not quite to that fixed point to 6 places after the decimal. Maybe if I go to 50, we will be. No, it's still not quite. 200 maybe. I mean, it's converging more slowly. Yeah, I mean, after maybe about 150 iterations or something, we get to 0.655172. What about if mu is 3? Exactly. The fixed point still is at mu minus 1 over mu, which is 2/3 if mu is 3. 0.6 repeating, but will the iterations approach 0.6 repeating? Well, if they do, it's very slowly. What's going on there? The derivative is -1 in that case. The derivative at that fixed point. F sub 3 prime of 2/3 is -1. Check it by hand. If mu is 3, yeah, mu minus 1 over mu would be 3 minus 1 over 3, 2/3. 2 minus 3 is -1. You're going to get -1. That's the boundary between attracting and repelling, stable and unstable. If I pick a seed real close to 2/3, well, if I pick 2/3 exactly, it will always be 2/3 because it is a fixed point. What if I pick something close to 2/3, but not exactly equal to it? If it is going away from 0.6 repeating, it's very slowly. Let's try fewer 6s, but maybe not that many 6s. So 0.66. Yeah, it looks like it's going away. Looks like at the boundary, when mu is exactly 3, 2/3 looks like, based on this numerical evidence at least, that it's repelling. Technically speaking, if mu is slightly less than 3, even 2.999 or something, technically speaking, 2/3 should be attracted. Doesn't look like it is, though. Maybe I'm not close enough. Maybe that's the problem. Yeah, that's looking more like it is. That it looks like I'm close enough now. That it looks like these iterates are approaching 2/3, which does make you wonder if you go back to 3, will it truly be repelling or not? Yeah. It's hard to tell. Okay, let's not worry about it. Once mu gets bigger than 3, even 3.01, it's definitely repelling. And you can see, I went up to mu equals 3.01. The fixed point now is going to be 2.01 over 3.01, mu minus 1 over mu. 0.667774. So technically speaking, we should probably start closer to that. Yeah, those iterations are, boy, it's still kind of hard to tell. we went further away. I'm pretty sure they are going to go continue further away, further and further away. Yeah, they are, but slowly. So what happens at that bifurcation value? It's changing from attracting to repelling. Do we get a period 2 point? Remember period 2? Let's try mu significant, well, not super significantly bigger than 3. Let's try mu equals 3.2. Is there a clear period 2 point or not? Looks like there is. Look at that. Between about 0.7994455 and 0.513045. Looks like there's an attracting 2 cycle. Is there a way to find out exactly what that 2 cycle is? Turns out there is. What do you do to figure it out? Remember what we just talked about a week ago? How do you figure out what the attracting 2 cycle is? This is a concept you should know for the test in 9 days. We have to create a new function. I called it F2 last time. There's a book I have that writes it like this, makes the 2 a superscript, and puts it in square brackets, which is a little confusing because some people might interpret that as a power, f to the second power, or other people might interpret that as a second derivative. It represents neither in this context. F2 sub mu of x represents f mu composed with itself. F mu of x. Second iterative f, you could call it. Because that's what I'm doing when I do iterations, is I'm composing the function with itself. So this is a relevant thing to think about. Compose the function with itself. Like this. You could also use the circle notation if you like. F mu circle F mu of x. Not requiring that, but you could use that notation. It's not a multiplication. Not multiplying F mu of x times itself. It's not a derivative. I'm composing the function with itself. Actually, if you're in abstract algebra, it's like a group operation. Function composition. What does it equal? Well, there's the formula for F mu. Mu times x times 1 minus x. I guess I got to use that a couple times. Plug that function into itself. Like that. What is that going to give me? It's going to give me, I got to replace each of these x's with this entire thing, right? It's a little confusing. Mu times x, this x gets replaced with mu x times 1 minus x times 1 minus x. That x gets replaced with mu x times 1 minus x. Yeah. Really? There it is. There it is. I better simplify. Let's see, if I distribute the minus mu x through the parentheses here, it's going to give me minus mu x plus mu x squared. So ultimately I have a trinomial. This, is this worth expanding or not? I think it's worth expanding just to do it. And we will need to take its derivative. So yes, it is worth expanding here. This expands to mu x minus mu x squared. So what do we get? We've got mu times, okay, let me go ahead and just be careful here. I mean, I could factor a mu out of that if I wanted to, but let me not bother. Go ahead and multiply this out here, this binomial times this trinomial, right? So I can't use the ordinary FOIL method. Let me multiply each term here first by 1. Get mu x minus mu x squared. Then I'll multiply each of these two terms by negative mu x, the next term on the right. This times minus mu x is minus mu squared x squared. Gotta be really careful not to make a mistake here. And this times that, the two minus signs, see where I'm pointing? Two minus signs make a plus sign. I've got a mu squared, and again, I guess an x cubed. Now multiply each of these terms by the last term over there, mu x squared. Mu x times mu x squared gives mu squared x cubed. And negative mu x squared times positive mu x squared gives minus mu squared x to the 4th. Got a 4th degree polynomial here. Multiply this mu through. There's no constant term. That's nice, I guess. Mu squared x. These two terms can be combined. They both involve x squared. And also multiply by mu. Maybe I'll keep the minus sign out in front. I guess I get in parentheses mu squared plus mu cubed x squared. See how I got that? I factored the minus sign out. I also multiplied those coefficients by mu. Here are your two x cubed terms, and they're the same, giving you, when you add them, 2 mu squared x cubed, but also multiply by another mu, you get plus 2 mu cubed times x cubed. And then finally, your x to the 4th term, after multiplying by another mu, gives minus mu cubed x to the 4th. So this 4th degree polynomial is this function here. It's f mu composed with itself, simplified. Let's try to Mathematica to confirm. So I could use the subscript button if I like. I could call it f2 like this if I like. I'm composing f mu with itself, so I can do the thing. Semicolon suppresses output to get the next line of code. Maybe I want to try simplifying f mu of f2 mu of x. Mathematica factored that, so maybe instead of simplify, I want to expand f2 mu of x and check my work. That'll multiply it out. Did I do it right? Looks good. Mathematica didn't bother factoring out the minus sign and the x squared out of these two terms, but they would give you the same thing I wrote if you do. Looks good. What's the relevance of this again? We talked about this a week ago. What's the relevance of this function? What does it help us find? I mentioned it 10 minutes ago as well. 2 cycles. The fixed points of this function are either fixed points of f mu itself or 2 cycles of f mu. Why? If P is a fixed point of f, then it's also going to be a fixed point of f2. Because if you compose f with itself, when you plug in P, you'll still get P. So fixed points of F mu are also fixed points of F2 mu. But we also have these new points. The two cycle, pretend the two cycle numbers are called P and Q when you iterate F. So what I mean here is F mu of P equals Q, and F mu of Q equals P. That's going to mean F2 mu of P is F mu of P is F mu of Q is P. And the similar kind of calculation would show F2 mu of Q equals Q. So in writing all this, I'm assuming P and Q are different numbers, but I'm assuming there are two cycle of F that these equations are true. And they become fixed points of F2. So the fixed points of F2, again, are either fixed points of F or two cycle for F. Mathematica. Can you solve for where F2 of mu of X equals X? This is something new. Everything else we've done so far today, we've done before to some degree. Here's something new, I think. Maybe I hinted at this last time as well, but going a little slower now. Can it solve it? Amazingly, yes. There's 0, which is always a fixed point of F. There's mu minus 1 over mu. Two new fixed points of F2 must be the points that are two cycles for F. And these are different things. They're almost the same, except a minus sign there and a plus sign here. What would happen if I plot all these things as functions of mu? Let's try that now. Plot the constant function at 0, mu minus 1 over mu, these two things as functions of mu. Change this minus sign to a plus sign here. What am I going to see? Kind of looks like a bifurcation diagram. Started one at least. Let's label the axes. Axes label. Mu would be the horizontal axis. What's the vertical axis? It depends. Sometimes it's fixed points, sometimes it's period 2 points. Maybe I should just call it special points. When mu is between 1 and 3, the blue line and the orange curve are fixed points. In fact, they're both, and the orange one's attracting. The blue one's actually repelling. When mu is bigger than 3, the blue one and the orange one are both repelling. The red and green are attracting fixed points for F2, attracting two cycle for F itself. The word bifurcation means we've had a forking. Forcation is related to the fork. Bi means two, so we've got a forking into two branches, two new branches that weren't there before. Actually, in the ordinary bifurcations that you make with this kind of thing, when you get to mu equals 3, you don't bother drawing the orange one anymore because it's no longer attracting. Because usually when you make these bifurcation diagrams, you're not making them by plotting these kinds of functions. Usually it's based on numerical iteration. And you're looking for attracting fixed points or period 2 points, 2 cycles, or 4 cycles, or 8 cycles, or 16 cycles. And that's what you observe in the long run, and that's what the points that get plotted. So the middle one's not typically there, but I'm putting it in there anyway. It's just no longer attracting. Okay, what this is, I want you to understand how to interpret this diagram. So the first bifurcation point is mu equals 3. What's the next bifurcation value? Well, how did we find the first one at mu equals 3? We found it based on the value mu where this derivative equals -1 when you plug in the fixed point. It equals -1 when mu is 3. And when mu is bigger than 3, it's less than -1. Could we do something similar? Maybe with F2? Take its derivative and plug in P and or Q, the period 2 for F. Yeah, that's actually what you do. Oh, do I really want to take that derivative? Oh, it's not too bad. F2, the symbolism gets crazy. F2 mu prime of X. Take the derivative of this thing. Get mu squared minus 2 mu squared plus mu cubed X plus 6 mu cubed X squared minus 4 mu cubed X cubed. That's the derivative in general, but to think about stability, whether the period 2 cycle is attracting or not, I have to actually plug in the period 2 formulas, which were those crazy formulas involving square roots. I'm fine doing this by hand. I don't want to do that by hand. Ideal use of Mathematica. So, well, just in case you're still writing there it is. So what am I trying to do now? Let's plug in, say this one, into what? Into F2 mu prime. Simplify? Hey, it simplifies pretty nicely. How about that? Maybe unexpected that it would simplify so nicely. What's relevant about that? Whether it's between -1 and 1 or not is what's relevant, right? That's the key condition. How about plotting that as a function of mu? Oops. What's the relevant range of values? How about mu goes between 3 and 4? I don't want to go above 4 for a reason, but although it's not really relevant here. Maybe it'd be good to plot horizontal lines at 1 and -1 as well, although it's the -1 that's the more important one. So the next bifurcation, it seems, that's going to occur is going to occur when mu is around 3.45, it looks like, where these cross. If I wanted to figure out exactly, I'd want to figure out where this thing equals -1. Solve for where that is -1. 1 plus or minus square root of 6. The one that's going to be between 3 and 4 will be 1 plus square root of 6. That is the next bifurcation value. And yeah, it's about 3.45. That's our next bifurcation value. How are we doing? Can I clarify anything? What's really going on here? I've hinted at in another way what's really going on here. And by the way, if I plugged in the other one, the other period 2 point where I have a plus sign here, I actually get the same derivative value, I think. Yep. What's really going on here can be seen also if you plot both F and F2. Say, let me go ahead and plug in a decimal here, 3.44949. 3.44949. If I plot both of these, that's this kind of picture. I guess I also want to plot y equals x. And it is nicest if you use aspect ratio, arrow, automatic, make the axes the same. What we have here is, this is our bifurcation value again of mu, 3.44949. An approximation to it. The exact bifurcation is 1 plus square root of 6 is the exact bifurcation point. Effectively, at that value of mu, this orange graph, which has got roots at 0, mu minus 1 over mu, same place as the blue line crossing y equals x. And these 2 points, those are the period 2 points for F. At this point here and in this point here, the slope is -1. Looks close enough to believe it, looking at the picture. And that's where the change is occurring from stability to instability, attracting to repelling. And we'd get a period 8 point from that instead of period 4 instead of period 2, excuse me. If we did NestList, F sub 3 point, let's just do slightly less than the bifurcation value, say 3.44. We should observe an attracting period 2 point going back and forth between about 0.44 and 0.85. I mean, we're close enough to the bifurcation value that it's not 100 iterations is not enough to see it real well. So if we do 1,000 iterations and drop the first 950 of them, now we see effectively, yes, going between 2 points more precisely, 0.442193 and 0.848505. This is doing 1,000 iterations and dropping the first 950 of them, so we just see the last 50. On the other hand, if I go on the other side of the bifurcation value, say 3.46, then we should see a period 4. Yeah. So we've got 2 bifurcation values so far, 3 going from a period 1 attracting to a period 2 attracting, and 3.44949 going from attracting 2 cycle to an attracting 4 cycle. The next one goes to an attracting 8 cycle. Where does that occur? Well, now we're getting to difficult to deal with symbolically.
Sorry, this is nothing, but how do you add a subscript? What do you type as a subscript?
It's the writing assistant here.
Oh, okay.
This button right here. Control minus. And again, this writing assistant you can get from the palettes menu. There's also a classroom assistant and a basic math assistant. Maybe I should call it F4 of mu of x is where I compose F2 with itself. Would there be an F3? Well, you could do an F3 where you compose F with itself with 3 Fs. But since what we're observing is period doubling bifurcations from period 1 to period 2 to period 4 to period 8 to period 16, it's going to be quicker to just think about the 4th iterate instead of the 3rd. So I'm composing F2 with itself. Fixed points of this would correspond to fixed points of the original function, period 2 points of the original function, and period 4 points of the original function. What is its formula? We really want to see it? Yeah, I can't resist. There's its beautiful formula. It's a 16th degree polynomial. Can Mathematica find its fixed points? Well, sort of. Four of them are easy to find. They're the same 4 as before. The rest are written with this root thing in there. And what in the world is that? Well, 16th degree polynomial is going to have 16 roots, though some of them could be complex numbers, and some of the roots could be repeated, having multiplicity greater than 1, if you know what that is about. I won't go into details right now. This is just Mathematica's way of somehow representing these other roots. Let me go back up here. Let's see. Let me give this plot a name. Let me call it plot 1. Can I possibly get Mathematica to plot these other roots as functions of mu? I tried it ahead of time. You can. What should I do? Well, the only difference between them in Mathematica is comma 1 versus comma 2 versus comma 3, etc. at the end. So what I tried ahead of time and it worked, was I copied and pasted this thing. I called it root n mu like this, and changed the 1 to an n. Now let's just get rid of this output. And amazingly, when I plot this thing as a function of mu for any n, it does work. Let's combine it with plot 1, with show here. Show combines plots. For example, if I type root 1 mu, mu goes from, what was the window here? 1 to 4. And I'm showing plot 1 in here as well. There, this piece gets added. Now you might wonder why is this vertical line in here? I think that's because it's actually going down to some other root, but we don't actually see it here. It might be too small of a piece of the graph to actually see, but I think that's what it's doing. Don't worry about the vertical line. I could also do root 2 of mu in there. Yeah, don't worry about that vertical line either. Root 3 of mu. Don't worry about the green vertical line. Okay, so I could keep going here and do more of these. These are supposed to be period 4 points that are tracking not over the entire range of values of mu that you see. What happens if I keep going here? It's not really adding more to the picture except on the very lower right corner here, which again are going to be there. I think they are there in the bifurcation diagram, but it's not really what we're focused on. We're focused on mu just barely bigger than 1 plus square root of 6 here, just barely bigger than 3.449. Focus on this part here. It's an attracting period 4 point. Where would the next bifurcation value be? Here's something I haven't tried. Let's try I'm probably not going to, this is probably not going to work. If I try F4 mu prime of root 1 mu, I think it's not going to, this is not going to probably do anything, or if it does, it's going to be weird. Yeah, okay. Can I still plot? It's giving me some sort of plot. It's hard to know how accurate that is. I'm also interested in where it crosses -1. Let's just go to 3.6 here. So this is the fourth iterate derivative evaluated at one of these roots, and also the horizontal line at -1. For the next bifurcation value, it should be where they cross. Looks like it's about 3.54, maybe. Would solve work to find it? I'm not sure. I'm trying things without knowing if they're going to work. Solve does try to solve things symbolically. Yeah, I think that's going to give us trouble. What would be better is find root. Let's see, abort evaluation. Okay, let's try find root instead. I got to give it an initial guess. Looks like close to 3.54 should be a good guess. Yeah, okay. 3.54409. Is that right? Maybe Wikipedia knows. Wikipedia. Search for logistic map. Blah, 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 blah. Oh, wait, what's that? 3.54409. That's the next bifurcation value. And in the bifurcation diagram, where is it? This thing. At 3.54409, which is just barely to the right of of this other one, right around here, I'd want to draw more branches for the period 8 point that would arise. Attracting period 8 point. And I could keep going. What's Feigenbaum's constant? Well, remember from the video, the Veritasium and number file videos, you're looking at the horizontal distance between where these bifurcation values are and looking at their ratios. So again, the first bifurcation value was at 3. The next one was at 1 plus square root of 6, which was again that. So the distance between that is that. The distance between that bifurcation value and the next one at 3.54409 is this. What's this ratio? 4.75. You might recall from the video that Feigenbaum's constant was like 4.669, etc. It's not too far away. Here, I try to find the next bifurcation value. Let me try. Okay. I'm not sure if it's going to work. F8 mu of X is F4 mu composed with itself. I can type. Can I do this kind of thing with F8? Mu is slightly bigger than 3.54. How much bigger? Well, if the Feigenbaum constant is to be believed, Here's the distance between these last two bifurcation values. It's close to 0.1. Should be maybe about 0.02 for the next distance, close to that, 0.025. If the Feigenbaum constant is close to 4.5. So what that's telling me is I should try maybe 3.56 here. Oh, no, there's a problem. This means the same thing I did before. Okay, so that's a problem. F8. I got to figure out the fixed points of F8 first. Maybe it's not going to work. What degree polynomial is F8? I think it's 256 degree. Yeah, I think I probably better abort evaluation. Okay, it's not going to work. Or if it does, it's going to take an inordinate amount of time. I think the next bifurcation value is near 3.56. Does Wikipedia say? I see there's close to 3.56. Is that what they're talking about there? No, that's the onset of chaos. What's the next bifurcation value? Doesn't look like it's right there. Oh, how about Google? I am gonna join Chat GPT this week. I wanted to make an account. Could ask Chat GPT if I had an account. List bifurcation values or points for logistic map. Wolfram Math World. Looking for like 3.56 in here somewhere. Not seeing it. I'm sure it's somewhere on the internet. Well, if we just pretended it was 3.56, how close would we be to Feigenbaum's constant here if we did it? So the next ratio, I'd want to compute this now in the numerator. And 3.56 minus 3.54409 in the denominator, which is not going to be exactly right, but okay, that can't be. Yeah, that's okay. It's too big. Must be slightly bigger than that. No. I'm artificially trying to get close to Feigenbaum's constant here. That's too big. Okay, we're getting close there. I mean, this is artificial. You know, maybe it's 3.5642. Because again, Feigenbaum's constant is supposed to be close to 4.669. Let's just look up Feigenbaum constant. The first Feigenbaum's constant is 4.669. And the amazing thing about all this is supposed to be that this is a universal constant. In the Veritasium video, they talked about how it comes up in lots of physics problems. You observe it in nature. And it's also emphasized in both videos that this period doubling root to chaos, where you're looking at these period doubling bifurcations and the bifurcation values where they occur and looking at these ratios, leading to this Feigenbaum constant, they occur with other kinds of maps, not just this logistic map. This logistic map is just sort of the simplest example, where you can actually do a lot of the algebra that we're doing here. So it's not easy. You can do numerical approximations for other examples that still lead you to the Feigenbaum constant. This period doubling root to chaos, and we aren't even at the chaos yet, right? this period doubling root to chaos arises everywhere.